Hello and welcome to this lesson for GCSE Triple Science in the radioactivity topic, looking at aspects of safety around exposure to ionising radiation. So there's a starter question on the screen here which relates to radioactive decay equations that we studied before the Christmas break. So have a look at that question and see if you can work out the answer. Pause the video to think about that. There are 3 marks for this question. Okay, so let's have a look at the answer to that. I'll just turn my pen on. There we go. So we need to look at this decay equation and we need to think about what's changed. So you can see that we start with an atom of radium and it becomes an atom of actinium. So it's a different element. And in that decay, the atomic mass or the mass number has not changed, whereas the atomic number has gone from 88 to 89. It's gone up by 1. So that's gone up by 1, and that is no change. So we need to think about which of these 3 it is. So with decay equations at GCSE, it's generally not gamma. Gamma, remember, isn't a particle. It is an electromagnetic wave. So the radioactive decay equations only involve either alpha or beta particles. So remember that an alpha particle is the nucleus of a helium atom. So it is a helium nucleus with a mass of 4 and an atomic number of 2. So 2 protons plus 2 neutrons giving a mass of 4. Whereas beta, on the other hand, is a high energy electron which has got a mass of a mass of 0 and effectively an atomic number of -1 because it makes the atomic number here go up. So which of these is it? Has the mass gone down by 4? In which case it would be alpha radiation, but it hasn't, has it? It's not changed. What's happened is the atomic number's gone up, so it must be beta radiation. So I said there are 3 marks for this question. 1 mark for saying beta. The other 2 are for saying a couple of these other things. So how do you know? Well, the atomic number has gone up by 1. You could say that would get you a mark. What else could you say? You could say the mass number is not changed. That would get you another mark. So there's your 3. You could say, for 2 marks, you could say that a neutron has split to form a proton and an electron. Okay, so in this question you're expected to interpret this equation here to work out what the type of radiation produced is. Okay, so that was just a little bit of revision. Let's get on to what we're going to look at in the main part of this lesson. So we're going to look at the units of activity and dose, and we're going to think about how radioactive sources are handled safely, and then how we judge risk from the exposure to ionising radiation. We've covered some of these aspects before. What the bit we haven't really looked at is what we mean by dose and risk. So let's think about activity. So that chap there is Henri Becquerel. He in fact was Marie Curie's boss at the Sorbonne in Paris, what he is associated with the units of activity of radioactivity. It's quite an honour in science, obviously, to get a unit named after you because of your contribution to science. So 1 becquerel measures how active the radioactive isotope is, and what that is really is a rate, the number of decays per second. So in science, in physics particularly, the units that you should always use for time are seconds. So if it's a rate of decay, then it's the number of nuclei decaying per second. Just like when you're looking at speed in science, if you give units of speed, it's meters per second. So the units of time are always seconds. So activity measures how quickly something is decaying, an isotope is decaying. It doesn't tell you really how dangerous or otherwise that might be. We need a different thing for that. That's dose. So activity is about how quickly it's decaying, whereas dose is about the harm that it might cause you. So if something's exposed to radioactivity, it might be contaminated. And what that means is if some radioactive substance attaches to something else, so it's mixed in maybe, or if you are exposed to, hopefully not, to a radioactive isotope, maybe a powder, and that powder gets onto your skin or gets inside your body, you are said to be contaminated, and that means that you contain these radioactive isotope, these radioactive atoms, which will decay and give out radiation. That's not the same as that word, other word in red, irradiated. That just means exposed to radioactivity. That doesn't mean that you've become radioactive. So radioactivity will kill cells, and that's obviously going to cause you harm, but it also causes long-term harm because if it damages the DNA of your cells, then it can cause cancer. So exposure to radioactive isotopes does have some risk, and we need to make sure that we don't have too much risk. So how do we handle radioactive materials safely? We've looked at this in the classroom and I've demonstrated, but we need to basically reduce the amount of radiation that the person receives. And some people have to be exposed to radioactivity as part of their job, and it's a really important aspect of their job to absolutely reduce that exposure as small as possible and to monitor their exposure, so to make sure that they haven't received more radiation than they ought to. So the dose, which is measures the possible harm, is got different units. That's called sieverts. So the more sieverts of radiation that you've been exposed to, the more possible harm there might be. And really, the way that this unit is used is to compare it to something else, to say the dose is equivalent to something else, and then that lets us make a judgment about how safe that thing is. So when we're handling radioactive materials or ionising radiation, there are four things to think about. First of all is necessity. Any person should only be exposed to ionising radiation if there is a good reason for it, if it is essential. If it's not necessary, then that person should not be exposed to any radioactivity. So, for example, if you go to the hospital, they don't give you an X-ray unless you actually need one, unless there's a suspected injury. Similarly, if you go to the dentist, they don't give you an X-ray there unless you actually need it. So that reduces your dose. Remember that X-rays are ionising radiation, a bit like gamma rays, but obviously they're not part of radioactivity per se. So how else, if you've got to have, say, an X-ray, how do we reduce the dose from that ionising radiation? Well, the first thing is to use shielding. So if you've ever had an X-ray in hospital, you'll know that you get like sometimes a sort of a little blanket. It feels quite heavy because it's got lead inside, and that is placed over any part of the body which should not receive any radiation. You can see in the photograph there, the radiologist is preparing to give the patient an X-ray, and when the X-ray is done, at that moment that the X-rays are fired from the camera that she's holding in her hands there, she will usually go and stand behind some lead shielding, which will reduce her dose from the radiation. The next thing is time. We keep that time to an absolute minimum. So when I demonstrated the radioactive isotopes in the classroom, I only had them in the classroom for the duration of my demonstration, and then they were put away again immediately. And then the final factor is distance. The further away you are from a radioactive source, the smaller the dose that you receive. So when I was handling the radioactive isotopes in the classroom, I used the long forceps and I held them at arm's length, and I made sure that you were sat even further away than I was to make sure that your radiation dose was as small as possible. So anyone who works with ionising radiation will have a film badge, which is inside that badge is a piece of photographic film, and it's in complete darkness, but when any ionising radiation gets to the film, it will darken the film slightly, and the more radiation that the person has been exposed to, the more that film will be darkened, and from how dark the film is, it can be found out how much radiation that they've been exposed to. So these badges are collected in and they're analysed to make sure that the worker isn't receiving more radiation dose than is safe for them. Okay, so the radiologist will move away, often to another room. They'll stand behind a LED screen. The LED is built into the walls there, and they've got a film badge which will monitor their radiation. And to keep the time to as short duration as possible, the radiation source is only switched on at the moment the image is taken. Patients are protected by only having an image when it's medically important. A minimum number of images are taken, no more than necessary. Certain body organs may be shielded, particularly the ovaries in a woman or the testicles in a man. That's because that radiation can damage the sex cells, and that could potentially cause damage to an unborn baby. In fact, if you ever have an X-ray, if you're a female, you will be asked whether it is possible that you're pregnant, because the ionising radiation, X-rays, an example of that, are particularly dangerous to an unborn child. Okay, so the idea then when we're talking about exposure to radiation is risk versus benefit. So any exposure to ionising radiation poses some risk, and we have to think about, well, how big is that risk? And we have to think of it as like a probability, a chance of some ill effect. So the bigger the risk, the bigger the chance of something bad, like unfortunately getting cancer, might be. And we have to compare that to the benefit of the ionising radiation. And we have to think that the benefit of that must be bigger than the risk to the patient. So let's have a look at an example. So I told you that dose is measured in sieverts. Now a sievert is often divided up into smaller units. So to make the numbers a bit easier to understand, I've given the values here in nanosieverts. Can you see on the table there the small n prefix to the SV, nano? A nano is 10 to the minus 9 of something. So 1 nanosievert is 10 to the minus 9 sieverts. Okay, so 98 sieverts is the radioactive dose that you receive if you eat a banana. Now, most people would consider eating a banana to be a pretty safe occupation, but it actually contains a radioactive form of potassium, which could potentially cause you some harm. There is a risk, but that risk is very, very small, 98 nanosieverts. Most people would agree eating a banana is pretty safe. And you can see there are various other things going on there, different doses, ranging from going through airport security to much higher risk things. So, for example, if you received a dose of 4,000 million nanosieverts, that is 4 sieverts, isn't it? That's a fatal dose. In other words, within 30 days, you'd have a 50% chance of dying from that dose of radiation. So clearly we hope that no one experiences such a high dose. But other things in between obviously do cause us concerns, and we use the idea of sieverts and comparing to something else to judge whether the risk outweighs or is outweighed by the benefit. So for example, what is the risk from a dental X-ray? So we can look at the table of information there, and we can see that the dose from a dental X-ray is 10,000 nanosieverts. Okay, so let's compare that to something else. So if we would compare that, say, to airport security screening, that's got a dose of 250 nanosieverts. So if you divide one by the other, if you divide 250 into 10,000, we would say that one dental X-ray is the same risk as going through airport security 40 times. So you can see, well, there is some risk, isn't there? It's certainly a higher risk than going through airport security, but we don't worry too much about that. And 40 times, well, I should think there are many people who go through airport security more than 40 times in a year. So there is a risk, but it's not a very big one. We could look at it another way. We could compare it to eating bananas. So we could say if you ate 100 bananas, that's the same risk as having one dental X-ray. Well, 100 bananas is quite a lot to eat, isn't it? But it doesn't seem particularly risky thing to do, so that perhaps puts the risk in context and might reassure someone who was a bit worried about the risk from a dental X-ray. Another way of looking at it is if you compare it to something with a higher dose. If you look at the annual dose for airline cabin crew, 1.6 million nanosieverts, well, that's regulated, that's checked, that's safe, and you can see that's a much bigger figure than the dental X-ray. In fact, it's 160 times bigger. So if you had 160 dental X-rays, that's the same radiation dose as airline cabin crew. And so you might say, well, airline cabin crew receive that dose regularly and they seem to be okay. And you'd need to have 160 dental X-rays to be the same as that. So you might decide that having a dental X-ray is pretty safe. The risk is low enough to be outweighed by the benefit of checking that you haven't got a cavity in your tooth. So there we go. That's the idea of using sieverts as a radiation dose to judge the risk from an exposure to ionising radiation. What I'd like you to do is I'd like you to open the worksheet which goes with this video, and there are some questions here which are in the same sort of vein as what we've just talked about. And you open it onto the Word document and write your answers onto the Word document, and then you can upload that back onto class charts, or you can take a picture of your answers and you can upload that picture to class charts. Either way, I'd like to see your responses, please, and I'll give you some feedback on that and also some house points. Okay, thanks very much. See you next time. Cheers for now.